So 9.3 is reciprocal functions. Update your table of contents and your title page. And so this is a new function for us. So we have to write down the parent function information. But the nice thing about it, though, is the transformations are the same process that we've done before. H goes left and right, K goes up and down. So this should be really instilled in you at this point. H goes left and right, K goes up and down. And the H is opposite of what you think it's going to be. So copy those down as well. And here's our first example. So determine the values of x for which it is not defined. Well, a function is not defined when you're dividing by 0. So we need to decide what would make the denominator 0. And since it's a polynomial, a trinomial, we'd set up our t-chart, think about that, and factor it. What adds to 5 but times to negative 24? So 8 times 3, 8 has to be positive, 3 has to be negative. So what would make that 0? Well, if the first part was 0, it would be if x equaled negative 8. The second part would be 0 if x equals 3. So those are the values where the function is undefined. So now go to your left page and try this one on your own over there. All right, that example 2. Now this one we have a graph, and it tells us our function right here, 3 over x minus 2, and we need to identify the asymptotes. Well, an asymptote appears when a function is undefined, so when the denominator equals 0. So this denominator equals 0, x minus 2 equals 0, when x is 2. That looks like a negative 2. Let me erase that. So there is an asymptote at x equals 2. Maybe that should be a colon rather than an equal sign. Then we have to define the domain. Okay, the domain is when you have a line going through this way. When is this going to be touching the graph? Actually, I'm going to redo that line and make it a little bit straighter. All right, so now it's touching the graph here. It's touching the graph here, here, here. It's touching it over here, but the one spot it's not touching is right here at 2. So what we could say for the domain is x given that x does not equal 2. So a vertical line is math notation for given. It's a shortcut. It just helps you write it a little bit quicker. And there's the bell. Okay, let's go the other way. The range is this way. When is it? When is it touching the graph? It's touching here, and it is touching here, or it's touching up here, but it is not touching there. So the range is when y, but technically we should call it, instead of y, f of x, just for technicalities, is for all f of x given that f of x did not equal 0. So now looking at that though, we actually discovered that we have a second asymptote. Asymptotes can be more than just where the domain doesn't equal it. It also is when the range doesn't equal it. So go back to our asymptote. So we're going to add another one. F of x cannot equal 0. If you were to put y equals 0, it's the same thing essentially, except for the correct notation at this point is f of x, and we probably should be moving towards that. Okay, example 2b. So let's take a look at this one. So where are the asymptotes? Well, we have one at x equals, look at the denominator, what would make that 0? Negative 2. And then there is another one right here, and we can tell that one by this. So it's f of x equals 1. Now remember, the denominator one is going to be opposite, but the constant added at the end is going to be the same sign. Okay, so think about that on this last problem. I'm going to jump back again. And what was the value that was added on to the end of this expression right here? Plus what? And the answer would be plus 0. That's why we had a second asymptote right there. Okay, so then the domain. If you've got your asymptotes figured out, the domain and range are much easier. It's all x's given that x doesn't equal 2. Negative 2, I'm sorry. The range is all f of x's, all y's basically, given that f of x does not equal 1. All right, go to your left page and try the next two on your own. Okay, now we're to the point where we need to graph it. So you're going to need some graph paper for this. And the first thing that we need to do is find our asymptotes. Our asymptotes are at x equals 1. I'm sorry, negative 1. On your graph paper then, draw a dotted line at negative 1. We also have an asymptote where f of x equals 3. So now you go and draw a line, our dotted line at 3. Those are going to be our guidelines to make our graph. Now our parent function looks like this. And we have asymptotes running vertically and horizontally. Now the number up there, the negative 1, adjusts if it's a reflection or not, but it will also affect the dilation. At this point, all we're going to be concerned about is the reflection. In math analysis, you'll worry more about the dilation aspect of it. At this point, we just need to know, does it look like the parent function, or is it a reflection? A reflection would be if that number was negative. If it's positive, it's a parent function. In our case, it is negative. So we just draw a line that goes along close to our asymptote, then up like that. We don't know how close to get to the center. That's based on the dilation, the number 1. And then it goes like this. They should be somewhat symmetric, so the distance that you draw it from here should be about the same distance as there. Doesn't have to be perfect, but it should be pretty close. So there's our graph. Now the domain and range. It's all x given that x cannot equal negative 1. And the range is all f of x's given that f of x does not equal 3. Let's try another one. So we've got this problem, and we start by stating or figuring out the asymptotes. So this asymptote is going to be at positive 2. This asymptote is going to be at negative 1. And then we look up above to decide, is this going to be the parent function or a reflection? Since it is negative, it's a reflection. So you start down here, you head on up, and you go like that. Again, the 4 would affect the dilation, but we're not overly concerned at this point about that. Okay, go to your left side and try out this problem. And this one. Okay, moving on then, we've got a real-world problem. So we need to write an equation to represent time traveled between the two cities as a function of railroad speed. Well, this is based off of the equation, distance equals rate times time. That's just something that you need to know. So if you're not real familiar with that, it's just something you need to start memorizing. Distance equals rate times time. But we want to solve this as a function, time as a function of the speed. So we want time by itself. So we divide both sides by r, and our function is the time equals a distance of 25 divided by our rate. If we were truly going to write that in function notation, we would say a function of the rate equals 25 over r. I would take either one of those. So then we need to graph. So we'd figure out our asymptotes. So that's pretty easy. It's at 0 and 0. So we think about a dotted line at 0 and at 0. And 25 is a positive number. So that means it's the regular parent function. And it looks like this. And now, so we have the same problem, but explain any limitations to the range in the domain. Now, when you put it into a real world situation, it changes a little bit, because even though that you can find an answer over here, it doesn't really make any sense, because that's talking about a rate of negative. You can't go negative miles per hour. So anything over here does not apply. Anything over here does apply. So the real world application of the domain is when x, or r in this case, probably should write it as, r is greater than 0. Can't be equal to 0 because we know there's an asymptote there. And then the same thing happens for the range. The range is when f of r, or t, is greater than 0. Again, it can't be equal to because we know that there is an asymptote right there. It can't be equal to it. Okay, left page again then. Try that problem. And try that problem. So that is the end of 9.3. I'm sorry, yeah, 9.3. Okay, so write your questions and your summaries, and let me know if you have any questions when you get to class.